can start.
Okay. Welcome back, everybody. So in the last lecture, we talked about monotone dynamical systems. And we noted the connection to cooperativity. And also, we spoke about the comparison principle, and we applied all these results to the RFM, which is a cooperative dynamical, nonlinear dynamical system. By the way, can you hear me and see me okay?
Yes, no problem. Clear and loud.
Okay, yes, good, excellent. Now, we want to speak about something called monotone control systems. And this is very important because we will introduce here something called as part of talking about this, we will introduce a generalization of the RFM called the RFM with input and output. And once we do that, we will be able to connect RFMs into networks. Using the RFM I/O, we will be able to connect RFMs into networks. So first of all, we want to talk about monotone control systems. So what is the difference? Earlier, we had something like this, and we wanted to define when this system is monotone. Maybe I will write now. We had a system, I will write explicitly the dependent on time. We had a nonlinear system. X was, say, n-dimensional. And we defined what it means for the system to be monotone. Now, we want to add an input and also an output. And we would like now, after we added an input and output, we would also like to define that the system is in some sense monotone, but now not just a dynamical system, but a system with input and output. How can we define that it is monotone? How can we extend monotone systems without inputs and outputs to monotone systems with input and outputs, and then these will be monotone control systems. Now, for simplicity, I will assume that U is a scalar and Y is a scalar. Okay, this is mainly for simplicity. So we plug in, this is a number, for any t, this is just a scalar, and for any t, this is just a scalar. And we would like now to define monotonicity. So the idea is as follows. Earlier, we took two initial conditions, and we said, if the initial conditions are ordered for the system to be monotone, we require that the solutions are also ordered for any t. This is what we required earlier, just for the system to be monotone. We wanted the state vector to satisfy this property that if the initial conditions are ordered, then the solutions maintain this ordering for any time. But now things are a little more tricky because, first of all, we would also like this, first of all, this is clear. We want the output also to be ordered. When the state, now we also have an output. And when the initial conditions are ordered, we would like also the output to be ordered. That's okay. And this is just a scalar. So the ordering here is very simple. This is just smaller or equal between two numbers. But now we also have a control. So now what we would like to do is we would like to add that if we have two controls, also we have two controls, and we also like, now the condition is like this. If we have ordered initial conditions and ordered controls, U and V, then the solution corresponding, let me see just the notation, we write the phi later on. The solution corresponding to U, and this is the solution. This is the solution corresponding to initial condition P at time 0 and the control U. And this is initial condition Q and control V. And here also V and U. So now we assume that there is also an ordering between the controls. Now the controls are scalar functions, okay? So one control, I don't know, ut and also vt is some scalar function. So how to define this? Well, it's very simple. We say that the two controls are ordered and write like this if this holds for any time t. So for any time t, we have to impose now an ordering on the controls. Why? Because we want things to be ordered, but now things depend on the control. Earlier, they only depended on the initial condition. So we took ordered initial conditions. Now we also take ordered controls and we have to define an ordering. So this is the ordering. We say that U is smaller or equal to V if this holds for any time t. So U, this is U, is all the time smaller or equal to V. So this is V. Then the controls are ordered, the initial conditions are ordered, and we expect the solutions, the state variables to be ordered, and the outputs to be ordered, and then we say, so this is the definition of a monotone control system. Questions about just this definition and how it extends the concept of monotone systems to monotone control systems. Now, think of it as there is the input, there are the initial conditions. If both are ordered, and this induces ordering in the state vector and in the output, then we say that the system is a monotone control system.
Michael, I have a question.
Yes, please.
Does this U depends upon the state variables too, or it's just independent? It's just purely a function of T or something from another type dynamical
We
system?
assume that it is. Thank you, Aditi. Yes, that's a good question. Here we assume that this is independent of the state. Just a control. You have two controls as function of time. Depend on the state, and when they are ordered and the initial conditions are ordered, you expect to see that the system, the control system, preserves the ordering. Then you say that the system is a monotone control system. Yes, like this. They only depend on T, not on the state.
Okay.
Okay. Now, a sufficient condition for monotonicity of the system, well, this will not be very surprising. First of all, dfx to dx must be met. I'm sorry, but something went wrong with the... Hello? Yes, yes, yes. Yes, yes, thank you, Arvind. I'm trying now. Thank you. Can you tell me, please, I think my system went a little bit crazy. Can you tell me, please, what was the last part that you heard? More or less. Can you hear me and see me now?
Yes, sir, you are visible.
Excellent, that's very good. And can you tell me, please, where more or less you lost me?
Sir, please zoom out a bit.
Please what, sorry?
Zoom out.
Zoom out, okay, zoom out. Is this better?
सर zoom in कर दीजिए थोड़ा सा. Sir, please zoom in.
Zoom in. Is this okay?
Yes, sir.
Up, down?
Yes, okay.
That's okay now? Okay, and can you please tell me where was I when you lost the connection? When I lost the connection, more or less, so I know what to say again, what to repeat.
So I think the sufficient condition for monotonicity, the last two lines, from here we are not able to get it.
Thank you very much. Okay, so let me speak about the sufficient condition for monotonicity of the control system. First of all, we need df to dx, the Jacobian. This is the Jacobian that we already encountered many times. We need it to be Metzler for any x. This is natural because we needed this anyway, just for this condition when we compare to initial conditions, to ordered initial conditions. Imagine that you take two equivalent controls, U and U, then the dependent control doesn't matter because it's the same control, but you still need the monotonicity with respect to the initial conditions, and this is required, as we already saw. You also need now dfi to du to be non-negative, because when you increase u, you somehow expect x dot to increase. This represents the fact that when you increase u, xi dot will increase. This is needed because now you need also monotonicity with respect to increasing the control. And finally, you need the output function h to be increasing in xi again, because if you increased x, these two guarantee that you increased x, but you also want to make sure that you increased y. And in order, so x was increased, but to see an increase in the y, you need this condition for the output scalar function h. So it's not difficult to prove that if you have all these conditions, then the control system will be a monotone control system. So let's see a simple example. An important monotone control system is linear control systems. Here, x is in Rn, u and y are scalar, and c and b are also vectors in Rn. So I look at this system, a linear system, and you see now there is an input and there is an output. So let's see what these three conditions means. This condition says that A is Metzler. These are the sufficient conditions for the system to be a monotone control system. df to dx, I differentiate this. This is f. I differentiate it with respect to x. I just got a, and a must be Metzler. This was this condition. Now this condition dfi to du, df to du, will be just the vector B. So this vector must be non-negative component-wise. And the H to dx will be C or C transpose, maybe C transpose, also must be non-negative. So the vectors B and C must be non-negative entry-wise, and A must be Metzler, and then this will be a linear monotone control system. Now, let's see a very important, for me at least, example of a monotone control system, which is the ribosome flow model with input and output. So how do we define this? We take the standard RFM, let's again speak about the case n equals 3, just for simplicity. If you understand this case, then of course you will understand the case of a general n. First of all, we have to add an output. Well, the very natural output here is the output rate of ribosomes from the last site, which is also the protein production rate. This is a very natural output because think about connecting this. Suppose that the RFM produces some proteins at some rate, and these proteins affect some other process in the cell. So naturally, the density of proteins or the protein production rate would be the output to tell the other system or the other part in the cell to transfer the effect to another part in the cell. The meaningful thing is the protein production rate. Of course, this will be a function of time, yes? I don't write this explicitly, but this will change with time. So this will be a time-dependent control. A time-dependent output, I'm sorry, time-dependent output. This is the output that we add to the RFM. And in general, the output will be, in the general n-dimensional case, this will be the output, lambda n xn. And now we also have to add an input, so we will multiply the initiation rate by u. U again changes with time. And what does this mean? When u is small, then I have a small initiation rate, so it controls the initiation rate. And when u is large, there is a higher initiation rate. So for example, we spoke about ribosome recycling, where the ribosomes leaving the chain go back, and because of the physical structure of the chain, and go back and start again initiation at the start codon. So this we can model, for example, but saying that the initiation rate is somehow proportional to the output rate with alpha positive. This will represent the fact that as more ribosomes leave the chain, more ribosomes can connect at the start codon and initiate, and so the initiation rate increases. On the other hand, maybe in some mRNAs, the proteins that the mRNA produces actually inhibits its own mRNA. And then perhaps we can model this with something like this as an example. So the initiation rate will decrease now as we increase the output rate. More and more proteins are produced, but these proteins inhibit the initiation. So I will take something like a negative feedback here. When y increases, u decreases. So this allows us to close loops and to connect networks, to build networks of RFMs. And what I want to show is that, so this is called the RFM-IO, RFM with input and output. And what I claim, it's very easy to check, the RFM-IO is a monotone control system. So we can use these tools. I forgot to say that this notion of monotone control systems was developed by Angeli and Zonta in an important paper that has many, many citations. And in this paper, they showed something very nice about the feedback interconnection of two monotone control systems. I'm not sure I have time to talk about this, so I put it on the side at the moment. We'll see later on if I have time to go back to this. At the moment, I just want to define the RFM IO because this will be important in the next talks. And I want to show that it satisfies this property of being a monotone control system. So what do we have to check? We have to check that the Jacobian is Metzler, but this we already know. When we checked that the RFM is a monotone system without control, we already checked that J is Metzler. So this we know. We have to look at dFi to du. dFi to du. So let's see what this means. Here, this is F1, this is F2, and this is F3. U appears only in F1. So in general, this will be 0, and that's okay. The only thing we need to check is dF1, where this is not 0. What is it? We differentiate this with respect to U, we get this. This is always non-negative because x1 is between 0 and 1, and lambda 0 is a positive constant. So dFi to du is always 0, or this quantity which is non-negative. And finally, we have to check dH to dxi. So this is d lambda 3 x3 to dxi. So it only depends on x3. So the derivative with respect to x1 will be 0, to x2 will be 0, and to x3 it will be lambda 3, which is positive. So it is always non-negative. Yes, again, when I differentiate with respect to x1 or to x2, I get 0. When I differentiate with respect to x3, I get lambda 3, which is positive. So obviously, this condition holds, this condition holds, this condition holds, and we showed that the RFM IO belongs to the class of monotone control systems. And what does this mean? So what does this mean? Just to understand, it means that if we take two controls for the RFM, say U1T, which is smaller always than U2T, so we take two controls that actually control the initiation rate, and one of them is all the time larger than the other. And we take two initial densities, P and Q, in our state space, which is the n-dimensional unit cube. So this represents one density, the initial density in all the sites. It is every density is between 0 and 1, and this is another density. This is exactly like in the good traffic day and the bad traffic day that we spoke about. This one represents a situation where everything is more dense than here. Then the solution emanating from P using the control U1 will be smaller or equal, always like this for every T, which is very natural because, first of all, this situation is more jammed anyway, and also I increase the initiation rate. So more ribosomes enter the system. So it's very natural to conclude that I will have monotonicity in the state vector. And of course, I will also have monotonicity in the output, because the output is just a function of x3. We already know from here that here x3 will be larger or equal to the value here. So the output, which is just X3 multiplied by a positive constant will also be larger. So I think we see that the RFM-IO is a monotone control system, and it's very natural to understand why it is a monotone control system. Okay, as I said, I don't want to talk too much now about the properties of monotone control system. It was only important for me to define the RFM-IO with the input that controls the initiation rate and the output, which is the protein production rate, and to show you that this is a special case of a monotone control system. And if we have time, we will speak more about what this means, but in any case, we now have the tools needed to build networks of RFMs, and also to close the feedback, positive feedback or negative feedback from the output of the RFM back to its input. And this has, of course, biological meaning and biological motivation, as I explained to you, because the proteins that the mRNA produces, or the output rate of ribosomes, of course, they have influence on other processes in the cell, other mRNAs, and now we can build networks representing these relationships, and in this way, perhaps, get a model for large-scale translation in the cell, rather than working with just a single RFM, which represents what happens for a single mRNA. Of course, in the cell, the mRNAs are not, there's not just one single mRNA working in isolation. There are many of them, and they are interconnected, and the network is a better model for what happens inside the cell, of course, and also a more interesting model. But before we go there, I want to speak about spectral analysis of the RFM steady state. This is also a very important notion. We go back now to a single RFM, and we know that in this RFM, everything converges to the unique equilibrium at an exponential rate. This is for any A in my state space. And we know this from production theory. We also know this without the rate from Jiang theorem. But if this converges to it an exponential rate, this means that after a short time, relatively short time, XTA is already very close to E, to the steady state E. So by trying to analyze, by analyzing what happens at the steady state, we will get a good description of what happens in the RFM, because after a short time, what we see are densities that are very close to the equilibrium value. Now, from the RFM equations, let me write them again, because by now I know them by heart. And maybe you also know them by heart. Again, just for this three-dimensional case, for simplicity. Now, from these equations, at the equilibrium, what happens? Let me switch back maybe to a better marker. At the equilibrium, we have lambda 0, 1 minus E1 minus lambda 1, E1 minus E2. Lambda 1, E1, 1 minus E2 minus lambda 2, E2, 1 minus E3. Lambda 2, E2, 1 minus E3 minus lambda 3, E3. At the equilibrium, all the derivatives must be 0. So what does this equation mean? This equation says that at the equilibrium, when you have equilibrium here, and equilibrium here, the input rate, lambda 0, 1 minus E1, is exactly equal to the output rate, lambda 1, E1, 1 minus E2, and this is exactly equal to this rate, and so on. So all the rates are equal. And because the rates are equal, the densities remain constant. So the water flowing in is exactly equal to the water flowing out, and so the density remains constant. Now we can write this equation like this. This is equal to this, which is equal to this, which is equal to this. But this representation is not very useful. We can extract an equation here for E3, a polynomial equation. We can extract a polynomial in E3 only, and then solve this polynomial and get a value for E3, and then get E2, E1, and find the unique E where all the entries are in 0, 1. We can do that. In our case, in this is 3. But this doesn't provide much insight on where is the equilibrium, and in particular, how it depends on all these rates. What happens if I change one of the rates? What will happen to the equilibrium? How will it change? This set of equations is very, very, provides very implicit information and is not very useful for us. The spectral representation is a much more useful representation. Actually, it is a representation of these equations, but it is much more useful. So to state the spectral representation, I first of all need to give you the Perron-Frobenius theorem, which is a very important theorem in the analysis of matrices. Undoubtedly, the most important theorem in the analysis of matrices with non-negative entries. So let A be a real matrix, n by n, with all the entries non-negative. This means that I look at this component-wise. So I look at all the entries, and all the entries are non-negative. And suppose, okay, let me do it like this. Let's assume that all the entries are positive. Then it's actually Perron theorem, but okay, that's good enough for us as well. Define the spectral radius of A as the maximum on all the lambda i's. I take all the eigenvectors. No, I take all the eigenvalues, lambda I, or the eigenvalues of A. And in general, they can be complex numbers. They can be complex numbers. And then I take the absolute value of these complex numbers, and I take the maximum. So let's, okay, I'll make an example in a minute. Then, if A is positive, there exists A admits a real and positive eigenvalue that's denoted sigma, which is just this rho of A. And the corresponding eigenvector V satisfies that all its entries are positive too. All its entries are positive. So let me try to explain what this means. I will erase these equations even though I need them later on. First of all, let's take an example, okay? Let's take an example where A is not positive, and an example where A is positive. So here, the theorem will not hold, and here we expect the theorem to hold. So here we can take, I don't know, 5, 1, 1, 4, I don't know. And here let's take 0, 1, minus 1, 0. Let's start with this example first. In this case, let's calculate the eigenvalues. So I calculate the determinant of this matrix, which is S squared plus 1, right? So the eigenvalues are J and minus J, and the spectral radius is the maximum of the absolute value. So this will be 1. It is the absolute value of j, which is 1. Or the absolute value of minus j is also a. So here the spectral radius, this is not an eigenvalue. So in this case, the spectral radius, which is the largest on all the modulus or absolute values of the lambda i's, is not an eigenvalue at all. 1 is not an eigenvalue. The eigenvalues are just j and minus j. But here, if you calculate the eigenvalues, you will see, I didn't make the calculation, but you will see some, so I don't know, look, let's say that this is very, very small, then the eigenvalues are probably something very close to 5 and something very close to 4. And then rho A is 5, and this is exactly lambda 1. And if you calculate the eigenvector, you will see that the eigenvector has strictly positive entries. So the eigenvector will be something like 1 epsilon with epsilon positive. So this is what the theorem says. If all the entries are positive, there is a lot of spectral structure. The spectral radius is also a positive simple eigenvalue, and the corresponding eigenvector has all its entries positive. And why is this true intuitively? Let me also give an intuitive explanation, and then I will give time for questions. So the idea is like this. This is just some intuition. Consider for a moment the dynamics x dot equals ax. So often I like to give dynamics using dynamical systems. So if you start here somewhere, I claim that when an A is positive. If you start here somewhere, I claim that you will always stay here. We know this because A is Metzler, right? If all the entries are positive, then in particular, the off-diagonal entries are positive, and they are non-negative. So A is Metzler. So for a positive initial condition, we stay positive all the time. Now, the idea is like this. If there was an eigenvalue like here, j or minus j, that was dominant, so if the eigenvalue with the maximal modulo was a complex eigenvalue, what does it mean, a complex eigenvalue? A complex eigenvalue corresponds to somehow making circles or spirals. But if there was a dominant complex eigenvalue, I would make spirals, but that's impossible because I know that when I start here, I remain in the positive ortant. I remain in the first ortant, so I cannot make spirals. Also, if there was a dominant eigenvalue which was negative, what would the dominant eigenvalue which is negative mean? It means just a minute here, I'm not sure what to say. Yes, maybe. Just a minute. No, this, I don't know exactly how to explain that the maximal eigenvalue must be positive. This gives some intuition why the maximal eigenvalue cannot be complex. The dominant eigenvalue, the one with the maximal modulus, cannot be complex. I think there is a simple reason why it cannot be also a negative number, but now I forgot what it is. I'll think about this and maybe mention it in the next lecture. But anyway, this is what the theorem says, and we will use it in a moment for the RFM. Questions about this Perron theorem. And sigma, by the way, is called the Perron root. of A. Questions? Well, maybe some of you, of course, know this. It's a very classical result. Now, we give an application. This is theorem 13 in the lecture notes that I've sent you. Consider the RFM with n sites and rates. The rates are always positive. Lambda, this is the vector of all rates, lambda up to lambda n, and all of them positive. Let E denote the unique equilibrium. So this is the point. We already saw the equations defining this E, but the equations we had are not so enlightening. Okay, now what does this theorem say? Define an n plus 2 by n plus 2 symmetric matrix like this. This matrix will be called A. Let me define it. First of all, on the main diagonal, I put zeros. So far, so good. On the super diagonal, I put lambda 0 minus half, lambda 1 minus half, lambda n minus half. The other entries above the super diagonal are 0. And because the lambda i's are all positive, lambda I minus half, which is just 1 over the square root of lambda I, of course, is well defined. This is well defined because the lambda i's are positive numbers. On the sub-diagonal, which is here, I also put the same thing because I want the matrix to, so I get a symmetric matrix. And all the other entries are 0. So this is a tri-diagonal matrix. Only entries on the first, on the diagonal, super diagonal, main diagonal, super diagonal, and sub-diagonal are non-zero. All the other entries are 0. So this is symmetric. And of course, it is component-wise non-negative. Now, the version of the Perron theorem that I gave you required A to be positive. This is not the case here. But if A is not negative and irreducible, which I didn't define, then that's enough. And the Perron theorem, the theorem, Perron-Frobenius theorem also holds. So we know that there is a Perron root, the maximal eigenvalue, and V be the corresponding eigenvector. So what does this mean? This means that AV is equal to sigma V. Sigma is the positive eigenvalue, which is also the dominant eigenvalue, and there is a corresponding eigenvector V. So AV is equal to sigma V, and from the Perron theorem, we know, Perron-Frobenius theorem, we know that we can choose the eigenvector V such that every entry in V is positive. How am I with time? I'm okay. Okay. Then the RFM equilibrium points satisfy EI is VI plus 2 divided by lambda 1, lambda I half, sigma VI plus 1. So this is a little miracle. We can express any of these EIs as a function that depends on the lambda i's from the RFM, we know them, and also the Perron root sigma of this matrix, and the vector V, the Perron eigenvector of this matrix. So it's a little strange in first sight. What is the connection at all between the equations EI for the RFM? In this dynamical system, we converge to EI, and here we have something entirely different. We take a matrix, we plug in all the lambda i's, we compute the Perron root and the Perron eigenvector, and then from this Perron root and Perron eigenvector, we claim that we can get every value of the steady state EI in the RFM. And I here is 1 from E1 up to En. This is called the spectral representation of the RFM steady state because it depends on the spectral properties of some matrix. So obviously, this is why we call it a spectral representation. I want to prove this because otherwise it seems a little bit strange that we have this connection between a dynamical system that converges to some equilibrium point and the Perron root and Perron eigenvector of this specific static matrix. So I want to prove this. Just let me see how am I with time. And should we start today or not? So let's, today I just want to give an example. I just want to give an example with an RFM with two sides. And in the last lecture, tomorrow, I will prove this, okay? Just to make it clearer. I know that it looks a little strange. So let's make an example in the 10 minutes or so that I have left. If I'm wrong with the times and I have more time or less time, then please tell me. I always get confused. I think it's okay. I have until 2:30. Okay. So consider an RFM with two sides and with all the rates equal to 1. So I took an RFM with all the rates equal to 1, dimension n equal 2, and all the rates equal to 1, so it looks like this. Now the steady state equations, when I put here E, I get E1 minus E1 equal to E1, 1 minus E2 equal to E2. These are the steady state equations, and we know that from any initial condition, we converge to this steady state. So from this equation, I get E1 is E2, 1 minus E2. And now I can substitute this in the other equation, and I get 1, I get this. This is an equation in E2 only, and this gives a polynomial in E2. And then when I solve this, I get that E is approximately 0.618, 0.382. So in this case, the equations just give me a second order polynomial. There are two solutions, by the way. But when I calculate for E2, I go back and calculate E1, there is only one solution in the unit cube. And this is the solution. So what this means is that in this RFM, if we wait long enough, the density in the first site will converge to 0.6, and in the second site to 0.3. And when this happens, the flow in and the flow out are equal, and so we stay with these densities. The densities are not equal, even though the lambda i's are equal, because of course, if you have some density here, usually you will have a smaller density here because this reservoir feeds this one. So in the second one, we expect usually less, smaller density. So we calculated E directly. And now let's try to do this using the spectral representation just to see that we get the same thing. So A now will be 4 by 4 because it is always n plus 2 by n plus 2. And we put there all the rates to the power of minus half. but because all the rates are 1, we get this matrix. This is the matrix, which is in this case 4 by 4. I just took all the rates, but all the rates are 1, and build this matrix A. Now I calculate the Perron root, so the maximal real eigenvalue of this matrix and the corresponding Perron root, and I get the following: sigma is 2 cosinus pi divided by 5. So this is a positive number. It doesn't matter exactly what it is. And I also calculate the corresponding eigenvector from this equation. And this gives me sinus pi divided by 5, sinus 2 pi divided by 5. Of course, such matrices are very special. 3 pi divided by 5, and 4 pi divided by 5. Of course, such a matrix will have very special eigenvalues and eigenvectors. So it's written sinus pi divided by 5, sinus 2 pi divided by 5, 3 pi divided by 5, and 4 pi divided by 5. So this is V1, this is V2, this is V3, and this is V4. And now let's try to see what this equation gives me. E1 is V3 divided by lambda 1 sigma V2. Yes? By this equation, this is what I get. And if I substitute all these values inside there, you will get this. And if you substitute E2 is V4 divided by sigma 2 divided by half. Well, the sigmas are 1, so you don't care about them. The lambdas are 1. And here you have V3, and if you substitute all these numbers, you have all the details in the example. This is example 16 in the lecture notes. So you get exactly the values EI that are the steady state values in the corresponding RFM. And if you had here lambda I is different than 1, you would just plug them in here to the power of minus half, and you will get exactly the same result. So let me just summarize. In the next talk, we will put this, but just to summarize, you have the RFM, you can simulate the RFM and see to the value of the steady state value it converges to. But of course, for a large n, this can be pretty complicated. Well, you implement some MATLAB, say, simulation and wait for a long time. Not always you know what is a long time, and not always you know the required accuracy. Or you can solve this set of equations, but this is very, very cumbersome. And this gives you an alternative approach. Forget about the RFM, just take the rates and put them here in this matrix. Calculate the Perron root and the Perron vector, and then you will have all the EIs in the RFM just by looking at this equation, calculating these values. And one big advantage of this is that even for large values of n, there are efficient numerical algorithms for calculating the eigenvalues and eigenvectors of such a matrix. So even from the point of view of just numerics, if you just want to know the E, it is better to use this. But of course, this has also many theoretical applications. But even in terms of numerics, this is more useful than any other approach for calculating E. Now, I remind you that in TASEP, when all the internal hopping rates are equal, and only in this case, there is a very nice representation of the steady state in terms of products of matrices, but usually these matrices have to be infinite dimensional. So I don't know exactly if there is any connection between, what exactly is the connection between TASEP and RFM is a big question. And if we prove something for the RFM, can we deduce something for the TASEP? Or if we prove something for TASEP, can we deduce that it works for the RFM? These are all open questions. But it is interesting in some way that here you can use matrices somehow to know what is the steady state of TASEP. And here you also can use this matrix, which is very different from the matrices here, to get information on the steady state of the RFM. So in the next lecture tomorrow, I will prove this result, just to show you where it comes from. And the idea is very simple. If you look at these equations, you can transform them so they look exactly like the equations for E. With a little bit of massaging, these equations are just the equations we have for the steady state equilibrium E in the RFM. We will do these calculations, and then you get that by doing this, you get that the EIs must satisfy this. Okay, that's a very good time for questions because we conclude now this talk, and we will meet again tomorrow. Please.
Any questions from the audience side?
Yes, please.
There is no question at this moment, but still, if you have any questions, you can directly write to Michael, and then we can get them.
Yes, you can also send me an email as well.
Thank you, Michael. So let's close this session for today. See you tomorrow on the session. See you tomorrow.
Thank you very much, Arvind. See you tomorrow.